Okay, welcome to our continuation of talking about physics. This section is on energy and work. So let's start off by asking you, what is work? Well, if I ask this question to you, I'd probably expect you to talk about homework, chores, sports, a lot of stuff out there probably counts as, for physicists, what we're looking at specifically is work as being done when an object is moved over a distance. Okay? So if you took a can of soda from a counter and you picked it up and you walked somewhere with it and you put it down, that is what we're going to look at as work. Okay? So, the ability to do work is called energy. Okay? So you have work, which is moving stuff, and then we have this thing called energy, which is the ability to basically move stuff. Pretty simple. So you can think of work as a transfer of energy. So when you do work on an object, you're going to transfer some of your energy to that object. Okay? So some of your energy went into picking up the Diet Coke can, getting up, walking it out into the other room, putting it back down. Okay? You transferred your energy to move the Diet Coke. Okay? Same thing happens in, let's say, air hockey. Let's say I put a lot of air hockey pucks out there and we start letting the air hockey pucks tap into each other, right? Or pull when you have the balls collide with each other. The energy of one object is transferred to another object and they all start to move as a result. Okay? So work is basically this transfer of energy causing things to move around. Okay? The unit of measurement is called the joule. It's one of those ones you got to memorize. The symbol for it's capital J. So you'll probably see that in some of the problems we do as we go through here. So first off, we're going to talk kinetic energy. So kinetic energy is the energy of motion. So here we got a couple of cars pictured. Motorcycles and Humvee 2, I think. That's an H2, yeah. The amount of kinetic energy an object has depends on two things. Its mass and its speed. So if these two objects were moving at the same speed, okay, then realistically they'd still have different amounts of energy because they have different masses. And intuitively you probably realize that. If you're in a larger car, an SUV, you probably have more kinetic energy even though you're going to the same speed limit as a much smaller car. Okay? Kinetic energy is going to be 1/2 mass times velocity squared. Your basic kinetic energy problem looks like this. You got a car traveling with a velocity of 40 meters a second and it has a mass of 1,120 kilograms. So we take the kinetic energy as 1/2 mv squared. Substitute in your 1,120 and your 40. Calculate that out, and this is probably something you're going to want a calculator for, as your number is 896,000 joules. Okay? Pretty straightforward. Very large car there. Alright. Weight versus mass. Mass is how much matter something has. Okay? So we're looking at the atoms there. Weight is slightly different. It has kind of it's a type of force vector, realistically. If you want to find your weight, you multiply your mass by your acceleration. Okay? So, since gravity is always pulling us down on Earth, your weight's generally kilograms times 9.8 meters per second squared, the force of gravity. However, we're on the moon, my force of gravity would be very different. So on the moon, your weight is different than it is on, say, Earth. Okay? And that's pretty important for when we talk about potential energy. So potential energy, as you can see here, the potential energy is equal to the mass times gravity times the height for an object that is placed up high. So we basically say that an object has potential energy when they either store it through their position, in which case we would use this equation here, or their shape. Okay? So when I talk about shape, what I'm really saying is springs. So springs have potential energy because their shape can be compressed. So because I can push down on a spring and have it pop back out, there's a kinetic energy I can store there. And you're kind of going to explore that a little bit in our next lab here with the kinetic scars. So you're going to see that the more you wind a rubber band, okay, the more potential energy you create, hopefully the more kinetic energy you see. Okay, so we'll get there in a second. This equation, of course, relates to the potential energy of an object if it's placed on something like a shelf or held over a cliff. So it'd be equal to its weight times its height, because mass times gravity gives me my weight. So usually in these problems you'll see someone's weight and how high they are, and you basically just multiply them. Here's a sample problem. A baby carriage is sitting on top of a hill that's 21 meters high. The carriage with the baby weighs 12 newtons. Newtons are a pretty unfamiliar version of weight, probably to you. Your weight in the American system would be a foot-pound, so kind of weird to say foot-pounds. So we'll actually be using newtons a lot. We'll talk more about newtons in the next chapter as well. So your potential energy is equal to your weight times your height. So in this case, we've got 21 times 12, which is in fact 252 joules. Okay. Energy can be transformed. So the total potential and kinetic energy of a system is called its mechanical energy. Okay. So your mechanical energy is equal to the sum of your potential and your kinetic. As an object rises or falls, the object would experience a change in its kinetic and potential energy. So if I'm falling, my kinetic energy is increasing because I'm moving, right? I'm accelerating. There's a velocity going on, okay? So I'm spending my potential energy to become kinetic energy. So you kind of create like a roller coaster physics sort of idea here. Which is why we had a picture of Space Mountain. So the law of conservation of energy says that when one form of energy is turned into another, no energy is created or destroyed. Basically, the law of conservation of energy says that we can have all this potential energy and we can turn it into kinetic. Okay? We don't create new energy in the process of doing that. We don't destroy the energy somehow in the process of doing that. We just change it from one to the other. So the total amount of energy in a system is the same before and after a transformation. Okay? So you have literally that roller coaster, and you're just going up and down and up and down, and you're just transferring potential to kinetic and potential to kinetic. And just this huge transformation over and over again.